Hello, my chemistry freshmen. Here is the walkthrough of our thermochemistry final review. So, first question states, describe what the system means in a thermochemistry problem. Describe what the surroundings mean. Remember, we said system is what our focus is on, and our surroundings are everything else. So, when we are looking at these problems, system is what we're focusing on, surroundings are everything else. So, for number 2, it says, what is the flow of energy in an endothermic reaction? What is the flow of energy in an exothermic reaction? So, endo kind of gives it away. Endo sounds like in a little bit. So for endothermic, it is in. So there's more energy going in. And an exothermic kind of sounds like exit. There's more energy going out or released by the reaction. For number 3, describe what occurs in an exothermic reaction. So in class we had talked about energy going in to break bonds and being released when bonds are made. In an exothermic reaction, energy has to go in to break the bonds for the reaction to start. When the new bonds are formed, energy is then released. If energy is flowing out in an exothermic reaction, that then means more energy is released in bond forming than used in breaking. So it is always a net amount of energy. There's always energy going in to break bonds, always released when bonds are formed. But if more energy is released when it is formed, we would be exothermic. For the next question, it says describe what happens in an endothermic. It would be the opposite. More energy is used to break bonds than is used to form them, or then is released to form them. So for an example, let's say we had a reaction where 10 joules of energy go in to break bonds. So draw it over here, 10 joules going in. So down will be in. That's to break bonds. Because remember, breaking bonds requires energy. So I use 10 joules, absorbing in. If, when I make new bonds, 5 joules of energy are formed going out, we took more energy in to break them than we did form them. In fact, we took 5 more. So this would be 5 joules for our example here, endothermic, because more went in. So if you can think of it in those terms, it's a good way to understand endo and exothermic. So the next piece of our review guide goes over the stoichiometry that we can do with energy changes. So the first one is basically what we've been seeing, like right here with the balanced equation, except for it is just written in a sentence. It says when 1 mole of CH4 is burned at constant pressure, 890 kilojoules of energy is released. Calculate the change in energy for a process in which 8.5 grams are burned. So we know that when 1 mole is burned, 890 kilojoules is released. That's our ratio. That is what we can do our conversion with. For the rest, we're going to figure out how many moles 8.5 grams is, and then we will convert from there. So I would start with my 8.5 grams. I can convert grams to moles, and if I look, C is 12, H is 4, so that is 16 grams is 1 mole. And then I know 1 mole releases 890 kilojoules. Now, be careful in a question like this. Releases means energy leaving the system, so it should be a negative 890 kilojoules. And if I just take my calculator and very quickly go 8.5 times a negative 890 divided by 16, you should get a negative 472.8 kilojoules. You could also write this as 478.2 kilojoules released. Negative, remember, is just our way of indicating direction going out. All right, and then for this next spot, it looks like what we have seen most commonly in class. It is a balanced equation with the energy. Now, the first question is saying, is energy absorbed or released? This is important because we need to know how to read this piece of the balanced equation. It is a positive 68, so that means, like our example right here, more energy was going in to break bonds than we lost going out. Our net difference is positive, and it's a positive 68. So because we have a positive value here, that means it should be written with the reactants, and it should be absorbed, or endothermic. For B, how much energy would be absorbed or released if 12 moles of NO2 were formed? Well, we know it's going to be absorbed because we figured that out here. So let's figure out how much energy will be absorbed. I'm going to start with my 12 moles of NO2. This one's a little bit easier than what we had up here because if I look, I already have a balanced equation that tells me my molar ratio. I know for every 2 moles that are produced, 68 kilojoules had to be absorbed. So I will say that for every 2 moles of NO2, 68 kilojoules is absorbed. I did not need to go to grams. I didn't need to do anything extra because I was already at moles. Hopefully you have this molar idea still in your head from second trimester, and you can quickly make these jumps. So I would go 12 times 68 divided by 2, and you would get 408 kilojoules, and it's positive, so it will be absorbed. And I'm going to write absorbed just to make sure. Now, 12 divided by 2 is 6. You could have multiplied it by 6 as well. Okay, for C, it is like what we did up in the question with CH4. Starting with grams, going to energy. So 32 grams of N2 are reacted with excess O2. Remember, this is just telling me I have leftover O2. And if you remember back to when we did limiting reagents, we can only get the answer from the limiting reagent. If I have excess, like I do in O2, it won't completely run out. We are basically telling you, in a bunch of words, all of N2 is going to run out. So this is the one I want to do my work with. I don't care about the O2 because it'll be left over. It's not affecting how much I can make. So 32 grams of N2. N has a molar mass of 14, so 2 of it would be 28 grams. That's 1 mole. And if I look at the balanced equation, 1 mole of N2 makes or requires an absorption of 68 kilojoules. So 1 mole of N2 requires 68 kilojoules. And if I do the quick math, it should be 32 times 68 divided by 28. And you should get 77.7 kilojoules. And it's positive, so it's absorbed. You should, on the assessment, write absorbed. Now, for D, this is like as hard as it can possibly get, because we have a container where we know the amounts of both of our containers. As we talked about in C, we need to know which one's limiting, because limiting allows us to solve for our answer. So I'm going to grab another sheet of paper, because we don't have a lot of space on this sheet here, to solve this problem real quickly. So what we have here is the question says we have 85 grams of N2. So let's convert that 2 moles. Now, we only have one product available if you're looking at the equation. It is 2NO2. So I'm just going to go to moles of 2NO2. So like we just did, 28 grams of N2 is 1 mole. And in this reaction, 1 mole of N2 makes 2 moles of NO2. I don't necessarily need to go to grams because I just want to figure out which one's going to run out first. So least amount of moles is going to run out first. For my O2, it says I have 65 grams. O is 16 grams, so 2 of them would be 32. And then if I look at the balanced equation, 2 moles of O2 will make 2 moles of NO2. And if I just do these two problems, so 85 times 2 divided by 28, that means 6 moles of this would form if all 85 is used. If all 65 is used, 65 times 2 divided by 32 divided by 2, only 2 moles will form. So, because this is the least amount, we have to pick O2 to be our limiting, because if all 65 gets used, I will only have formed 2. I can't get to 6. I can't even get to 3 because I run it at 2. So we know NO2 is our limiting, so we're going to do our problem. Sorry, we know O2 is our limiting, so we're going to do our problem with O2. So let's come back to the question. Slide it up here for you. We know we're going to use the 65 grams of O2. So 65 grams of O2, as we just established, 32 grams of O2 is 1 mole. And for every 2 moles that are reacted, 68 kilojoules is absorbed. So 65 times 68 divided by 32 divided by 2 gives us an answer of 69.1 kilojoules absorbed. So that's about as hard as it would get, because you would just need to determine which one will limit or affect the rate of our reaction. In this case, it would be the O2. Okay, let's move to the back. This starts talking about our calorimetry equations. And the first question states, how does a calorimeter work to show us the amount of energy released or absorbed in a reaction? If you remember to our example that we did in class or looked at the board, it was a device that has water in it. And whatever reaction happens, we measure how much energy the water absorbed. Because if the water absorbs 10 joules of energy, so let's say here's my reaction vessel, and then it's surrounded in water. If the water, we find out, absorbs 10 joules, and that must mean the reaction released 10 joules into the water. So it's a really good way of us determining how much energy something releases. Especially helpful in things like food, where we need to figure out how much calories are in the food product. We can ignite it in a calorimeter. It will release its energy, just like it would do in your body, and then we can figure out how much energy it gives your body, or how much energy your body needs to put in to break it down. Now, the next question says, describe what a specific heat value means. And it's really a specific unit that tells us how much heat energy it takes to raise 1 gram of a substance 1 degree Celsius. Remember, we also talked about heat capacity, which was just how much it takes to raise it 1 degree Celsius. We can get more specific, obviously, with the term specific heat, because it's dealing with 1 gram. And if we know the mass and we know the change in temperature, we can very easily determine the change in heat. So for the next question, it states what is the enthalpy, which if you remember is the fancy term for heat flow that we use in chemistry, in kilojoules. If 60 grams of copper, and it gives you the specific heat, is heated from 25 to 150. So we are going to use our calorimeter equation. We are going to use Q, which is heat, equals mc delta T. So we set this up. Mass is 60 grams. Our specific heat is 0.385 joules, which is important, gram degrees Celsius. So we've canceled grams now, top and bottom. And our change in temperature was 150 minus 25 because it's final minus initial, so 125 degrees Celsius. We've now, in turn, canceled our degrees Celsius. So if I do this math, 60 times 0.385 times 125, we get an energy of 2,887.5 joules. Now, this would be fine, but the question wants it in kilojoules, so we would need to divide that by 1,000, and we would get 2.88 kilojoules as our answer. Next one is similar, except for it's giving us a different variable to solve for. It tells us to calculate the mass of a lead sample when it loses 832 joules. So because it's losing, energy is leaving the system, we are negative 832 joules. We want to know mass because it says calculate mass. It tells me the specific heat of lead, that's why they put the PB down there, is 0.160 joules per gram degree Celsius. And it went from 85 to 24. So we go 24 minus 85 because it's final minus initial. And that's a negative 61 degrees Celsius, which is important because if we have negative negative, it'll give us a positive mass, which is possible because we can't have negative mass. So if I do my algebra right, I should go 0.160 times a negative 61. And that gives me a negative 9.76 m because I multiplied the mass. If I want to get m by itself, I divide that over. So negative 832 divided by negative 9.76. And our mass ends up being 85.25 with some rounding grams. Now, this next question is the best example of how we use calorimetry because it's having you put metal or some sort of substance in water, and we need to use how much energy the water absorbed, like we did up here, to determine how much was released. So the question states that a piece of metal weighing 59.047 grams was heated to 100 degrees Celsius and then put into 100 grams of water, initially at 23.7 degrees. The metal and water were allowed to come to an equilibrium temperature determined to be 27.8. Like we talked about last unit, the cooler one will get hotter, hotter one will get cooler, we'll find some sort of middle ground. That is our middle ground. If no heat was lost in the environment, that means the water absorbed all of the heat. So we need to find the specific heat of the metal. So let's figure out how much energy the water absorbed first. Flip it, because that's how much the metal released. So if I look, I know I have 100 grams of water. This is a number you're supposed to memorize. The 4.184 joules per gram degree Celsius. And then our temperature went from 23.7 to 27.8. So if I go 27.8 minus 23.7, I will get a change of 4.1. So 4.1 times 4.184 times 100 gives me 1,715.44 joules absorbed. So if the hot piece of metal, when I put it in water, allowed that much energy to be released, that should be the amount that the water absorbed. So let's flip our sign, negative 1,715.44 joules, and say, now this is how much the metal released. Let's find out what its specific heat was. And we know its mass. We don't know its specific heat, but we do know it went from 100 to 27.8. So we go 27.8 minus 100. That means it cooled 72.2 degrees Celsius. And if we do our math, C equals, we gotta go 59.047 times a negative 72.2. It's a negative, I'm going to write it up here just so I can remember, 4,263.2. I need to go the negative 1,715.44 divided by that negative 4,263.2. And we get a C of 0.4. Now, this is important because on a test, I could be given a table. That table could have a bunch of specific heats, and I could identify that metal. I could know what type of metal it was. So that's the wrap up of our calorimetry problems. To end it here, we then have Hess's law problems, and I'll just do a really quick kind of wrap up of these. Remember, Hess's law is a good way for us to solve enthalpy change because it doesn't matter how many steps it happens in. If the reaction happens in one step, or if it happens in 6 steps, the change in energy will always be the same. So scientists use these different steps to their advantage. And they know their changes in energy, and we'll just stack them up together so that way we know what it's going to be. So if we are looking at this first equation, we want to get these two data pieces that they gave us to give us this answer right here. We want this balanced equation. So if I look at this first reaction, my first suggestion would be find something that matches with the balanced equation. And there's two things. Actually, there's three things. There's C2H6O, right there and right there. There's O2. And there's H2O. But they're in the wrong spots. We need to flip them. So if I were to flip this equation, which I can do, I would need to flip the energy. If these two things broke down and reacted to make these two things, doing the opposite, breaking these two things down to make these two things, would require the exact same amount of energy. So that equation we're going to flip. So it should be we should flip it, and if we look, I have 1 mole here, I have 2 moles here, I need to multiply this by 2. So I'm going to multiply this whole thing by 2 and flip. So if I do that, I now have 4 CO2 plus 6 H2O makes 2 C2H6O plus 6 O2. And my delta H now has changed to a positive because I flipped it. And it should be 685.5 times 2, 1371. For the last one, it is also going to need to be multiplied by 2, because if I see right here, I have 2 C2H4O, and I only have 1 C2H4O there. So I need to multiply it by 2. In this case, I don't need to flip it because everything's in the right spot. So if I multiply that by 2, I got 2 C2H4O. 5 halves is 2.5. So if I multiply that by 2, it is 5 O2. 10 CO2. And if I look right here, that is 10 H2O. And my number should stay negative. I should just multiply it by 2. So it should be negative 1,167. Now, these are the only 2 steps that they gave us. So there's a good chance that everything cancels. So let's look. I have 5 O2s over here I can get rid of, and that leaves me with 1 O2. Perfect. I have if I'm looking, 10 H2Os and 6 H2Os. Oh, I'm sorry. This should not be 10. This should be 4. 2 times 2 is 4. 2 times 2, this should also be 4. That is my mistake. Those should not have been as large as I had made them. So 4 CO2 cancels. 4 H2O leaves me with 2 left over. That gives me my 2, 2, 2, 1. Just like I wanted, if you ignore my mistake. Sorry. And then I add my energy. And you should get 204 kilojoules. And it's positive, so that means energy is absorbed. For a time, I'm going to skip this last one because it's the same process. And as long as you are flipping and multiplying in the correct way, you're going to get that final answer.